You're welcome back again. So last time we give some introduction to cross-validation in machine learning. So we want to look at how we can implement this properly using neural network. So like I said before, cross-validation is a robust technique for evaluating machine learning models. And we are not going to look at only cross-validation alone, but also going to look at together with tuning. And we're going to use grid search to tune our data set, our model rather, so that we can see the best performance parameters in our model. So we're going to look at a 10-fold cross-validation for neural network on breast cancer data set, and with performance comparison against a random forest classifier. Okay, so now we're going to load our package. In case you don't have this package installed yet, you can install the packages by using this line of code, right? Just pip install them. So we run this line, right? So we added here SK keras, this Scikit-learn here for Sklearn compatibility with keras. We also added early stopping and reduce on the 2 for training optimization. All right, so all the necessary libraries that we need has been added here. So now we first need to load our data set, which you have used before. Okay, we load our data set here. So we have data set loaded. So our feature and the target is passed in as usual. Okay, so we're using 80% for training and 20% for testing. So we are going to stratify because of our data set that is imbalanced. Okay, so this is shape of our data set. We have 569 samples here with 30 features. Okay, so the rows versus column. Okay, we have features like radius, texture, and so on. So our class imbalance exists here. We have a 212 for malignant, and we have a 357 for benign. So the benign is higher. Okay, so it's not this is not severe. Okay, it's manageable, right? So that's why we just introduce our stratify parameters here, okay, as yes, so that it can handle this little imbalance situation. Okay, this is not a complex or severe imbalance situation, so we don't need to bring in smooth here, right? And the certify splitting is crucial to maintain this ratio in training test set. So that's why we use stratify here to maintain that. Okay, no need for resampling techniques such as smooth, since imbalance is moderate, right? So it's not too high. Okay, if it's too high, then we have to introduce smooth. Okay, stratified splitting ensures balanced class distribution in training set, and standard scaling mean of 0 and standard deviation of 1 is critical for neural networks. So we move on gradually now. So let us build our neural network with callbacks. So we enhance neural network with callbacks now. So we define our model. So our learning rate is 0.001. Our dropout is 0.2. So model is we call our model sequentially, and we pass in our parameters, our ReLU, our dropout, we pass it in. So I mean our activation rather. So this is what we have: 64, 32, and 1. So we have our optimizer to be Adam. So our learning rate is passed here. All right. Then we compile the model. Okay, so our loss is binary entropy because we are dealing with the binary data here. Our metric is accuracy. So we return the model. So our callback is called our early stopping. So we actually the layer 54 to 32 neurons with ReLU activation is our layers here. Okay, these two layers, you have the layers here, and the dropout is 20% rate to prevent overfitting. Okay, our dropout 20% to prevent overfitting. You can see our dropout here 2.2 means 20%, so that overfitting can be prevented. Sig mode for binary classification was used. Okay, right. Okay, so we have optimizer Adam with a customizable learning rate. All right, so this is our sig mode here. So now we are going to go gradually. So I'm just trying to give us the more information about the architecture of this particular model. So let's go gradually now. Looking at the model. So first, we are going to have this import at the top with other imports. So from here, we have this because of we want to use the history. Then we added this one later. So our LS stop here and reduce on the 2. So we initialize the history callback because we want to see the history of the data of the model. So with history callback now, we create an instance for the history. So we define the keras classifier with all callbacks. So we pass in our business. So our epochs is 200. Our batch size is 32. So we pass in our LS stopping here, which we have created before. Reduce on play 2. History callback. So our patience is 10 for this and 5 for this. Our variable is 1 because we want to see the process. All right, so we train the model here, putting the model here, passing the model parameter here. Validation is what to split is 0.2. Yeah, so then we say access and plot the history now. So history, we create a history data frame here. Okay, so we call the history here. We pass in our accuracy, validation accuracy. Our type 2 model accuracy is here. Then we pass in our loss and validation loss, type 2 validation loss. So we just plot the sort. So it's a plot. So our epochs is 200. Don't forget. So this is what we got. Can see that the training is not that bad. It's not doing bad at all. So this is what we got. So this can be improved upon. So this is there's hope that this can be better than this. You can see there's hope that it can be better than this. Can be improved upon. That's our accuracy, and likewise our loss. This is our loss. So it's not bad. So it can be improved upon. So now the early stopping hot training is if validation loss doesn't improve for 10 epochs. So that is purpose of early stopping. Actually, it halts the training. Okay, if the validation does not improve for 10 epochs, no, why is going? If you do improvement, then you have to halt it. Reduce on play 2 also reduces learning rate by 80% when loss plateaus, and enables keras native progress bar. So we can see the progress, and the validation metrics appear because we specify validation split here. We use 0.2. Then we also do our callbacks like early stopping. We print the action. So for good training, if accuracy increases steadily as we are training, as the model is being trained, learning is effective. Okay, so it's learning effectively. So if the loss decreases without spark, nothing that is mean there's no overfitting. Okay, so that's a problem when the accuracy stalls. That means we are going to try higher learning rates if loss oscillates widely. So we may need to reduce a batch size. Okay, so alternatively, we can also do our simpler approach by doing the training. So if we need to the full back core system, the full callback system. This will separate the plot actually, but no problem. We can call our create model here. Just make it very simple. The trend is here. So, and then we pass in our feature, our scale feature here. Our epoch is 0.200. Our split is 0.2, which is 20%. Our byte size is 32. Bubble is still 1. So we still have our plot. So now just plot here very directly here. I show the plot. I see the very simple line of code here to plot, which is we have our process here coming out. You can see our process here. Okay, so which is not doing bad as well. So similarly, is not bad at all. Okay, I see the process. So now this is the result output of this process. You can see. So it's not doing bad at all. Not doing bad at all. Accuracy and loss. It's not doing bad at all. And the validation accuracy can also be improved upon. It has some kind of a fluctuation here, which can be improved upon. Okay, you can see this one is okay. You can improve upon it a little bit. So now let's look at what our tuning system now. We use our upper parameter tuning by using grid search. So we get our parameter grid first by passing our learning rate 0.001, 0.01. We can add more to this if there is a need for it. So our dropout is 0.1, 0.2, 0.3. So we also have batch size 16, 16, 32. If you have more, and maybe you are dealing with some modern stuff like images and all like that, you can add more, increase batch size to 64 as well. Okay, so we pass in our grids, we build our grid search here by passing in the parameters we have built already. So we print our parameters here. So you can see here when we run this now. Okay, we start a parameter tuning here, so you can see it's building afresh again. You can see here, so you can see. So this is what we have. So after it finishes, okay. So now our best parameters here, can you see here? Batch size 32. The model dropout is 0.1. Model rate is 0.01. Okay, our learning rate 0.01 rather. So this is our optimal configuration. What we got. So see the learning rate 0.01 lower rates are often better for fine tuning. Okay, our dropout is 0.1. Moderate regularization prevents overfitting, and our batch size 32, which balances speed and stability. So our grid search tested 12 combinations now, which is 2 times learning rate times 3 dropout by 2 batch size. Now we have our propagation to be 98.5%, which suggests robust performance. Okay, so let's train the model now. We train the best model we are able to, based on the parameter we got here now. So we are able to train that model again now to see, now to have the best model. So our best model, we create a best model. We're passing our parameter grid here. So for the best model, we train it here now. So now you can evaluate the model now. Evaluate the model on a best parameter model now. So do evaluation here as usual. Then we print our classification report here. So we have our malignant and benign here, showing here. You can see the result here, what we got. So you can see our accuracy here. So the precisions, we have precision 7%, false positive here. All right, and for malignant, we have a 1% false positive for benign, which is critical. For recall, we have missed 2% malignant, and the cases for other cases, and we have 4% for benign. This is critical for cancer detection. We may need to do some retraining again. All right. So, and we can see here control matrix here. Okay, we got our control matrix function by passing our y-test, prediction here. We have plot our, make it very small so that it won't be too big. So you can increase the size here 10 by 8 or 10 by 7. So to make it a little more bigger for purpose of a manuscript or thesis or whatever. So we want to use it for. So we call we use our function, itmap function here to create our function matrix, so that this is a standard one which is better for publications. So we pass it here. You can see how we arrange it. So you can have multiple of that here. So this is our bar. It should look like a legend. Okay, so that's a progress bar. So we have false negative, which is 1, less critical in medical context. Okay, that's a missed cancer. Okay, you can see false positive. This is a false negative. Okay, Also have a false positive here, which is 3, all right, which is dangerous and critical. LV patient needs retesting, all right. So that is what it means. So you can see that is called false positive. Okay, I hope you to remember what it means, what false positive means, what false negative means. You can go back to my first video to go and understand what I meant by that. So we also have a ROC curve here. You can see ROC curve here. So we create ROC curve by passing our parameter in here. So we print our ROC curve and make it very small. So we just plot it using different kind of parameter we want. So you can change it where you want, the color, the everything. You can change it where you want. So now left for you. So this is our ROC curve 0.99. All right. So this is near perfect classifier, and because between 0.9 and 1 we have excellent discrimination. So curve hugs top left corner, which means high true positive rate at low false positive cost. And we also have for practical use, we can operate at high sensitivity points, which is 99% recall at 10% false positive rate. Okay, so this is what we have here of our ROC. Then we can now look at the classification of the best model now. Okay, you can see it now based on the 10 k-fold 10 split now. So our n split is equal to 10. All right, so that's what we have here. So we can want to pass this across to the CV, and then we can see our result. When we print our result after it finishes here, we have a 10-fold correlation with the best parameter model we pass in. Our accuracy is 98.5 approximately. Our standard deviation is 0.014. You can see that this one is very low, this one is very high. So which means that this particular compared to 96 we got before, okay, there's a lot of difference. 96 and 98.5 is not a small difference. All right. So we validate the model stability across different data splits. Now we use a certified 10-fold correct validation for reliable accuracy estimation, and we use our mean. We achieve 98.46 with our accuracy, our 1.4%. This is 1.4% actually. Okay, that deviation across folds. Okay, 31.4%. So inconsistency check, low deviation less than 3%. All right, which is good enough. Model performance is good across all data point split, right? Then if of course if that deviation is greater than 5, you have to investigate later heterogeneity. Okay, so let us compare with random forest now. Just call our random forest model here. We pass our estimators random state as usual. So we pass on our scale features. So we print our file data. We have our random. Can you see for random forest now? Okay, this is what we got. Okay, which is not bad. Excuse me, it's not bad at all. Alright, so what we got, so we can compare also with what we got previously. So with classification that random forest we have got a 96.2 and 0.33, which is high. Okay, high deviation here, which is greater than 3 already. Okay, can you see 3.4 approximately percent. Okay, so model does not perform consistently across data split, but manageable. It's manageable because it's already more than 3%. You can see here this 3.4. Okay, even though accuracy is a little bit high, so we need to investigate data heterogeneity. So let's look at feature importance for random forest now. To random forest, you can see that you can get our feature importance, which we have done before several times, if you remember. So just to know that which feature that contributes to these high accuracies, you can check that with a random forest feature parameter. So you can see our feature here. You can see those feature that are you can pick from here downward, right? So we have features such as worst area, we have worst concave points, and so on, right? So neural network accuracy is high, but requires scaling. For random forest, they use built-in feature importance, so no scaling needed, right? So our top features are recorded here. You can see them here. Worst radius, mean concave point, which this matches medical literature, okay, online. So the performance gap now is 98.5% of neural network performance, which outperforms random forest 96.3%, but with less adaptability. So when to choose, when do we choose random forest? We choose it when we need feature importance explanations, and when we need when we have limited computational resources. Because if we are dealing with a more complex data set or image base, we may need to use a lot of resources to generate them. So this is us. In summary, we have our early stopping prevent overfitting for us, which we saw in our neural network. We are our learning rate schedule improve our convergence, and our parameter tuning optimizes our performance. So in evaluation, multiple metrics such as accuracy, UAC, recall and precision give us and even ROC give us a comprehensive insight into our model. So this is just basically a complete pipelines in the data modeling, data training using neural networks with together with a co-validation and the tuning system, which is our grid search. So this is very interesting, but you can just plug in your data. So you don't need to do much. Just plug your data here and bring your data here. Okay, plug it in there and make sure that your data is fitting with this particular parameter set. So just plug in your data and you can run this easily. Okay, just run them. So you can eliminate the random forest part if you don't need it. It's not necessary. You can eliminate it. But this is a complete neural network pipeline, which give good results. So you can do some tuning to upgrade or improve on the performance, so that it can be some form of a little improvement. So if you prefer this particular simple method, you can use this one. If you want the plot individually, one by one, you can do that. If you want the plot combined together, you can use the second method, so which we used before. So this is what we have so far. And thank you so much for listening. If you have any question, any thing you want to say, you can just drop it in the comment section, and we'll see in the next class. So you can like, you can comment, you can share. And if you are not subscribed yet, you can do so as we continue in this journey and see more of this classes. So thank you so much. I will see us in the next class. Bye for now.